something very specific about orbits, and it has to do with going from one orbit to another orbit. And I wanted you to know 3 details. The first detail is that changing orbits is complicated. So you can't just go from one orbit to the other and like just, I don't know, point your ship where you want to go and get there. It's not like that. To go from one orbit to the other requires that you actually change your speed in a unique and kind of interesting way. And I don't want to make a big deal about it because it's really not probably going to show up on the exam. I mean, the AP exam. But I think it's important that we kind of at least discuss it because it has been on the AP exam at least one time in the past. So there are a couple things you have to know. First, if this is your ship and you're traveling in an orbit like this around a lower orbit, if you want to transition to a higher orbit, you actually have to increase your speed, which puts you in an elliptical orbit. But then when you get to the new orbit, the new place you want to go, in order to stay in that orbit, you've kind of got to get to a speed that's a little different than what you might expect. This comes from looking at the fact that we're dealing with the force of gravity and the centripetal velocity. If we want to get a relationship between how far out you are in your orbit, so comparing this R with this R, then we want to just observe how the velocity and the radius are related. Now, the overview requires that you remember this isn't radius, this is separation distance. This isn't separation distance, this is radius. We use the same R for both. You have to ask yourself before you take or answer the question, are they the same thing? Look, they're going to try and fool you on the AP exam. And I can't possibly predict every contingency. So I'm trying to give you little clues that you can use before you start. So are these the same value? If they are, you can proceed. If they aren't, you can't. So make sure you ask that question before you go on. I'm sure to probably manipulate that a bit on your upcoming test, just to see if you're paying attention. A little loud where you are, Vanilla. So if they are the same, then we can cancel one of them out. And also, I've tried to emphasize this. It doesn't matter what the mass of the object is in orbit. Small things, big things, they all orbit at the same speed because that mass cancels out. This cancels out because gravitational mass and inertial mass are the same. Again, a small detail, it's little, but on multiple choice, you'll miss that question. So I will ask a question like, why does the mass cancel out? And you could, if you say it's because it's the same on both sides, that's not the right answer. The right answer is because gravitational mass and inertial mass are the same thing. So a short answer question like that is sure to trip you up. And you'll just say, well, the M's cancel. Not good enough. So what we're left with is that the thing that really matters is the mass of the planet, whatever's at the center. And this is the first result that we did yesterday, indicating that if you go to a higher orbit, you actually have to slow down. R's in the denominator. So if R gets bigger, the velocity has to get smaller. There's 3 things you'd have to connect in an argument about why that's true if you can't use an equation. And like I said, it's quite possible they'll say to explain it without using equations. You would have to say that going further away makes the force of gravity smaller. That's the first thing you'd have to say. Getting further out makes the force of gravity smaller. The second thing you'd have to say is if the force of gravity is smaller, that requires less centripetal acceleration, which means you have to slow down. 3 things. If you don't include all 3 things, your explanation isn't successful. Now, I want you to go one step further than that even. which was to be able to describe the time it takes to go around your orbit. That means replacing the velocity with the circumference divided by the period. So when I do that, I get this 4 pi r squared over t squared. Now that doesn't say very much. It's hard to kind of understand what's related to what. So I want to change this a little bit. I'm going to cross multiply to distill it down a little bit. And I get mpg times t squared equals 4 pi squared times r cubed. That's a squared pi there. Sorry, squared pi. The equation isn't important. This part is important. These are constants. So I'm going to kind of ignore them for a minute. We want to talk about what's related. And the period is related to the radius in a weird way with a cube and a square, but they're related. And it means that if you want to go out to a farther away radius, then it's going to take you longer to go around the planet. That's how that's related. An increase in altitude requires an increase in period. Again, you need to explain the entire chain using some kind of verbal argument. And that verbal argument is almost the same as the last verbal argument, that going further away decreases the force of gravity. A decrease in the force of gravity has a decrease in the centripetal acceleration. That causes a decrease in velocity. And you have to add something here. You're going around a bigger circle, but you're going around it at a slower speed. So it's going to take longer. You have to say all of those things if you want to explain it on a test. You have to start with gravity, say how it's related to the centripetal acceleration, say how that's related to the velocity, and then say that going slower around a bigger circle takes longer. If you can say all of those, you're likely to get all of the points. This question was on the test a couple years ago. Asking a gravity-based question about orbits, they're not going to make you calculate it like we do on mastering. It's just not, they're not going to have you be tedious on the calculator. I just don't see it. I do see them asking questions like this. That's kind of been what their go-to has been. All right, so that's, we talked about that yesterday. I don't want to beat it anymore because some people have heard it now twice. Any follow-up questions about that? Okay. Today I want to be very specific and very focused. We're going to talk about work and energy. This is a new topic for our class. We just barely launched it yesterday, but today we're going to really flesh it out and talk about the specifics. I have a lot of specific definitions I want you to know, word for word. And I'm going to start with our definitions for work. Work is a technical term in physics. It's not ambiguous. It is very specific what it means. And I'm going to give you two specific definitions. The first is the one that I like the best, that work is the method by which you change something's energy. I'm not going to write all that down. I want you to write it down. Work is the method by which you change something's energy. It's a method. It's how. So it's a method by which you change something's energy. So any method in which you change something's energy is work. Now, this is something that is physical. We're talking about physical or mechanical energy. You've already had an entire course in changing something's energy. You guys had chemistry. And in chemistry, you change something's energy using a different process completely. And I don't want to spend a lot of time trying to draw this out of you, but can anybody name one of the processes by which you change something's energy in chemistry? You had three. Just have to drag your chemistry teachers in here. Those grades you got, David, what do you think? That's how you know if something's energy has changed. But how do you do it? You could, but that's not likely what you did. Oh, this makes my heart sad. If I give you one of them, you'll get the other two. Radiation. And there you go. Those are the three ways in which you can directly change something's energy. You can put it on something that's hot, that's conduction. You can put something hot inside of it and stir it, that's convection. Or you can put it in the sun, that's radiation. The three ways that you can change something's energy. So that is what work is in physics. The specific way you can go about changing something's energy in physics requires mechanical work. In chemistry, it was conduction, convection, or radiation. And although you could change something in an endothermic or exothermic reaction, which I don't even want to think about whether you know the difference between those two, considering that you couldn't come up with conduction, convection, or radiation. That just hurts my heart. But you should remember at least that if you want to change something's energy and make it hotter, you have to put it next to something hot. In physics, if you want to change something's energy, you have to push on it. It's that simple. Work specifically is any force used to displace an object. That's specifically how it's done. Any force used to displace an object. So the method is a force. It is the connection. But it's a force with a displacement. So that's how you do work in physics. That's how you change something's energy. You apply a force, and because of that force, the object's position changes. Now, I want to be very, very clear here. You can push on an object all day, and if it doesn't move, you're not doing any work. So if you lift up one of these tables and just stand there all day, you might get tired, but you're not doing any work. Work is about an object. Something changes about the object. So if the object doesn't change, if its location doesn't change, you didn't do any work. Look, I'm going to try and trick you on the next test, and I'm going to be good at it. So work is done by forces, and it's done whenever those forces are involved with a change in position. So what that actually looks like, very specifically, is that if you have an object and you apply a force to it, and I'm drawing that force at an angle on purpose. If the object's position changes, if it moves from here to here, then work was done by this force. The issue, though, is that the only part of that force that actually does work is the part of that force that's in the direction of motion. So the whole force doesn't do work, just a part of the force that is in the direction of motion. So when we write that out, we say that work is force times the cosine of the angle. That's the angle between the force and the direction it moves. The force is likely to move the object along the ground. So the angle that we're looking for is the angle between the force and the displacement. There are three parts to calculating work. Three parts to calculating work. Now, your book talks about it's the force parallel to the direction of motion, and they will write this out. Force with little parallel lines next to it. If you like that better, fine. It's still going to be the cosine every time. It will always be the cosine between the direction of the force and the direction of the displacement. It's built into the formula. You don't have to think about it. You don't have to decide whether it's sine or cosine. It's always cosine. So it's part of the formula. And we have to take a brief aside for just a minute to talk a little bit about this formula. So let's do that for just a minute. This is about units. First, force is in newtons, and displacement is in meters. So when you are doing work, the unit you have is a newton times a meter. Now, I told you units are weird in physics, so let's make sure we understand exactly how weird that is. That's kilograms, meters per second squared times meters. So this is actually kilograms, meters squared per second squared. It's a lot to take in, and we actually have a name for it. We call this the joule, not J-U-U-L. That's bad. You get in trouble for that. It's J-O-U-L-E, joule. It's named for Henry Joule, not that that matters. This is a unit of energy that we use in physics. You might have used it in chemistry, but you are more likely to use the calorie in chemistry. So I want you to know how they're related, because I believe it's important that you understand that joules and calories measure the same thing. You had two kinds of calories, I believe, right? You know the difference in big C calories and little c calories? These are the ones that are in food, and it takes 1,000 of these to be one of these. If you don't remember that, you'll need it for my class. But it takes 4.19 joules to be one little c calorie. That means it takes 4,190 joules to be one big C calorie. You need those conversion facts. I will ask about them. Now, that suggests that our unit of energy, the joule, is really small. It's the smallest one. And if you don't remember what a little c calorie is, I'm sad, because again, that hurts my heart. That's like all of chemistry. So if you don't remember what it is and can't write it down, you probably should write this down, because I'll tell you. I don't want to try and see if I can find one of you who knows it. So a little c calorie, it's the amount of heat energy required to raise 1 gram of water 1 degree Celsius. All right. Now, let's just do a little bit of a little play on this for a minute. Halloween was a couple days ago. Do you need me to say it again? It's the amount of heat energy required to raise 1 gram of water 1 degree Celsius. There's people who believe that you can lose weight just by drinking ice cold water. Human body, 98.6 degrees Fahrenheit. That's like 20 something degrees Celsius. So if you drank ice water, every gram of ice water is going to extract energy from you in order to be heated up to your body temperature. You can calculate how many gallons of water it takes to burn off one pound of flesh off the human body. Unfortunately, you'd have to drink enough water to kill you to make this a viable diet. So it's not a particularly good one, unless perhaps you're tripping on X or something like that and are really, really thirsty. It's unlikely to be the right kind of diet plan for you, but you could figure out how much water it would take if you really wanted to. So I'm a big fan of Kit Kats. Anybody else like Kit Kats? I don't share. So when I get a Kit Kat, it's all mine, all 4 bars. It's like 450 calories if you have all 4 bars. That's 450 big C calories. It's a lot. It's a lot. And for Halloween, I splurged and had an entire Kit Kat, like the big boy. So I wanted to go to the gym the next day so that I could maybe dispense with this 450 calories. And I was going to do so by doing bench presses. Now, this is a setup, but the bench press is the easiest setup for us to deal with because it's not a particularly hard calculation. I don't work out much, so I can't lift very much. Let's go with a cool 100 pounds. But we need this in kilograms in order to do this. So could you divide this by 2.2? That's going to give me kilograms. Come on, let's just make it 50. Won't that be easy? We'll say that the bar, it was in there, and now it's a solid 50. It's close. So close enough for me. So I put the weight on the bar, and I'm going to do a bench press. So I'm going to take, and I'm going to push up on the bar. I'm going to do work on the bar. Now, it shouldn't be hard to figure out that gravity is pulling downwards on the bar while I am pushing upwards on the bar. If I want the bar to go up, I have to push up with at least as much force as gravity is pulling down. So gravity is pulling down with mg. That's 500 newtons. I will have to push up with 500 newtons so that the bar smoothly goes upwards. Any problem with that? So I'm going to do, I have long arms. They're not quite a meter. They're 85 centimeters. So if I go from my chest straight up, I will move the bar 85 centimeters. That's 0.85 meters. Please do me a favor. Calculate how much work I did on the bar. It's not hard. The work I did on the bar is going to be equivalent to the force I applied, 500 newtons, times how far I moved the bar, 0.85 meters, times the cosine of the angle. Now let's pay attention to the angle. I pushed upward on the bar went upwards. So can we say that that's 0 degrees? That I pushed in the same direction the bar went? You need to evaluate this every time. So 0 degrees. So Eisen, how much work is that? Come on, Eisen, wake up.
It gives me 1.
It's not going to be 1. It's going to be 500 times 0.85.
Let me check again. Oh, yeah. Yeah, 425.
Right. 425. And the cosine of 0 is 1. So I can leave it like that. So this is 425 joules. That's how much work I did pushing the bar outwards. Now, would we agree that bringing the bar back really isn't done by me? It's done by gravity. It will pull the bar back. So I'm only going to count the outward push as something that's helping me burn off this Kit Kat of 450 calories. So each push is 425 joules. So let's find out how many bench presses I have to do to burn off a Kit Kat. We'll start by just doing some simple conversion. I want to convert joules to big C calories. So 425 joules, and I want to know how many big C calories that is. And let's just remember our conversion fact. It's 4,190 joules for every 1 big C calorie. How many big C calories is that per bench press? How many? 0.1 big C calories for every bench press. I would like to burn off 450 big C calories, and I only get to burn off 0.1 big C calories for every bench press. So could you divide 450 by 0.1? Don't use your calculator. You can do it in your head. You just move the decimal place over once, right? No, other way. 4,500 bench presses to burn off 1 Kit Kat. Is this the right way to exercise if your goal is to burn off the Kit Kat? No. Resistance training doesn't burn calories. Not the way you think it does. We're not doing anything fancy here. This is what the machine is doing. And anybody who's been on a treadmill or a Stairmaster or any of those kinds of machines, this is what the machine is doing. It's calculating the amount of tension or force on the platform and how far it moves. And it's converting it into big C calories for the display in front of you. If you have an exercise watch or anything like that, the first thing it asks you to put in is your weight. So it can calculate how much force you have to apply to your body to move it. And that's how it tells you how many calories you're burning when you walk, run, bike, or any other exercise. It's measuring how much you're having to move your body. It's got accelerometers in there to do that. And that's how it processes how many calories you're burning. You would never be able to burn off a Kit Kat by doing bench presses. You'll break your arms first. You can work out to lose, the amount of food you put in to burn off that energy, but it's unlikely you could do it by one exercise alone, especially a resistance training exercise. So don't try to do bench presses to burn off a Kit Kat. Go for a jog or a bike ride or a nice good walk. That'll have a much better chance of burning off those kinds of calories. You can't escape that this is the energy conversion. So no matter what you do, this is how the energy is used. Now, that being said, there's more to this than just calculating energy. And here's where I need you to get a little bit technical. We calculated how much work was done by us lifting the bar. But I said to you at the beginning of this, every force does work. There's more than one force on the bar. What's the other force acting on the bar? Gravity is the other force acting on the bar. So there's the work done by gravity. It's a different amount of work because the work done by gravity is 500 newtons times 0.85 meters. It acted the whole time. But what's the angle between the direction the bar moved and the direction of gravity? Could you say a little bit louder for our folks at home? 180. Thank you, 180. Cosine of 180 degrees. Vanilla, what's the cosine of 180 degrees? Maybe I'll get the impression that perhaps Vanilla doesn't know the answer or isn't actually.
I'm calculating it. It's
Okay.
a little slow.
You guys started the
Get
unit
a
circle.
-1.
It is -1. Have you guys done the unit circle yet in pre-calc? So this is one of those ones you're supposed to have memorized, right? Yeah, so it's a cosine of pi, same idea, it's 180 degrees, so it should be -1. So this means it's -425 joules. And this is going to bring us to an important conclusion that some work takes energy away and other work adds energy to the object. Generally, we're going to talk about this concept of net work. 2 words, not network like internet stuff, net work, the sum of the work. Work is a scalar. Positive work means you increase the energy of an object. Negative work means you took the energy away. While I was pushing up on the bar, I was attempting to give the bar energy. But the entire time I was doing so, gravity was trying to take that energy away. You know when an object's energies changed when its velocity has changed. I'm going to say that again because that's the important piece of today. I know I'm getting close to the end, but I still have 10 minutes. You know when an object's energies changed when its velocity has changed. There's some algebra that could show you that. It's not really worth it. This is called the work-energy theorem. And it states that anytime you do work on an object, you potentially could change its energy. In physics, we note a change in energy as a change in the kinetic energy. In physics, the simplest form of energy is motion, and we measure it by measuring kinetic energy. It is the basic building block of all energy in nature. Even all the energy you saw in chemistry could be boiled down to the motion of the atoms. So kinetic energy is the most basic form of energy. And if you don't remember from middle school how to calculate kinetic energy, it's easy. It's 1/2 mv squared. That's how you calculate kinetic energy. Now, a couple pieces here. This is the little stuff, the little tiny details that you know that I'm going to ask and harp on when we have our next test. The M here represents inertial mass. The more mass an object has, the more inertia it has, the more energy it's going to take to get it moving. That should make sense. It should be intuitive. If it takes more force to get that object to move, once it's moving, it has more energy. So that refers to its inertial mass. Please notice the velocity is squared. Remember yesterday we were doing those problems with ratios? This is another one of those things where we talk about ratios. How much does the energy change if you double the velocity? Well, it has 4 times the energy now, right? Remember we talked about that yesterday. If you double the mass of a planet, how much more gravity is there? If I double the velocity, how much more kinetic energy is there? So you know I'm going to ask that question on the next test too. When you do work, you're attempting to change the energy of an object. You hope to change its velocity by giving it kinetic energy. When I pushed up on the bar, I gave the bar 425 joules of energy. The problem is gravity took away 425 joules of energy. So the net work done was 0. When the bar got up there, was it moving? No, it probably stopped because I never changed its total energy. So we're going to talk about how we change energy of objects using work. And we're going to do this idea of looking at all the forces that act on an object and calculating how much work was done. The expectation here is somewhat straightforward. And I want to be very clear about what I want you to do. Let's take a simple example, because this is what I would say would be a good kind of starting test question. $5-kilogram box. $25 Newton force. 35-degree angle. I want to pull the box 10 meters across the ground. You guys take a minute and tell me how much work did I do on the box. I'm going to pick one of you. People at home, be ready. No cameras means you guys are first up. All right, that should be enough time. You're only punching a bunch of buttons. So Anna, what do you got?
I'm still punching the buttons.
Keep punching, punch faster.
So I had a question. So do we use the 25 newtons that are like the arrow, or are we converting the kilograms and then like adding it, or are we just using the 25 newtons?
You're just using the 25 newtons because I want the work done by that particular force.
Okay, and then so I got 2.0 because 25 times 0.1 because
Well, it's going to be 25 times the cosine of 35 degrees.
Yeah, and then
times delta x, which is 10 meters.
Oh, okay, so it's just that. Then why did we for the last one, like the Kit Kat one, we did 0.85? Oh, because that was the okay. Never mind, because you lifted it 0.85. Okay, I'm sorry, I got confused.
Okay, no worries.
So 204.8.
Andrew, is that what you got? Oh, he's not here taking a test. So I call in a kid who's not even in the room. That's a real bugger. So Jacob, is that what you got? 204? All right. 204 joules of energy. This is the work done by me on the box. When the box got over there, just want you to know, it was moving at 1.5 meters per second. What was the net work done on the box? No. I'm asking something that we've not practiced before, and I'm trying to see if you're really paying attention to what we talked about. And I don't know if you are, so I'm going to give you a hint. Net work is the sum of the work done, and it equals the change in kinetic energy. I gave you a velocity, but I didn't tell you if there's anything else doing work on the box. There could be. If you're asked for the net work, and put this in your notes because I'm not going to write it down. If you're asked for the net work, the first thing you should try and do is see if you can do the change in kinetic energy. It's the easiest thing to look for in any problem that we will have. So the box is now moving. So it has kinetic energy. It is always going to be easier to see if you can find the change in kinetic energy. Always. Always try for that first. So take a quick moment. Be fast, because I'm going to pick on one of you now. Ready? Noah, what was the net work done? 5.625 joules. Trevor, is that what you got?
Yeah.
Now, here's where I want you to be really, really sharp. This force did 204 joules of work. The box only has a change in energy of 5.6 joules. What do you think might have been acting on the box to take away energy? Friction is the most likely culprit. There was likely a frictional force that acted backwards on the box. Can you tell me how much work was done by friction? You should be able to. If not, look at this. There's the work done by the 25 Newton force plus the work done by friction had to equal 5.625. I just want you to tell me how much was this? You guys ready? I can pick on one of you. Caitlin?
I got it as negative 199.
Negative 199 joules. Yep. It has to be. It has to be negative. I don't think that part's a surprise. If the box moved to the right and we know friction has to be to the left, the angle between the displacement and the friction is probably 180 degrees. It had to be negative though, because we put this amount of work into the box and it didn't end up with that amount of work. So something took energy away. It's likely that it's friction. That's a good, good choice. Now you could do more here. We could set this equal to the frictional force times the displacement times the cosine. You could be asked to figure out, how much frictional force there was, but I want you to have the big picture here. Yes, ma'am. It's 9:17, so that means you guys have been a wonderful audience. I appreciate all of your time. Thank you for stopping me. Of course, you were supposed to stop me a minute ago, so I appreciate your bravery there. Hey, look at that. Even the bell's off by a minute. You guys have a good day.
Bye, Mr. Shelton.
Bye-bye, guys. It was nice
Bye.
to see. Well, it was nice to have you guys here.
Mr. Sheldon,
Yeah.
so with the bench press thing, the post